Right, welcome to today's class. We're going to be continuing on with natural deduction rules, but today we're going to have a focus on natural deduction rules with regards to predicates. Right, so remember, we talked of predicates and quantifiers at the beginning of this course, and we're going to have a discussion surrounding the natural deduction rules. Right, so let's see. We gave the definition of a predicate. We said it was an expression of one or more variables, right, defined in a specific domain, right? And then we had the universal quantifier being introduced, where we say that it will take the form and shape of that where x is to be a variable, and then we also know that this is called a predicate. Right, so all the information is known. We know that universal quantifier is represented by words such as all, every, each, any, right? And then we also have existential quantifiers, which are defined by words such as some, existence, at least one, n, right? Meaning there is something or an object that satisfies the given condition. Right, so that is what quantifier logic was all about. So now we need to look at the natural deduction rules surrounding that. So for a universal quantifier, we observe the fact that if we are saying something is true for all elements in the domain, if we are saying that something is true for all elements in the domain, it means that we can pick any arbitrary element, it has to be true. So what happens is that, and you're going to see it in a bit, is that we call this conjunction universal elimination, right? Where we eliminate the universal quantifier. Right. Now, to do that, before we look deeper into that, let's look at universal introduction. So we have, again, is an assumption that we have, right? If we assume that C, an arbitrary constant, is true, right? We are assuming an arbitrary constant is true. Arbitrary constant is true. Constant is true. Right. So, given that C, an arbitrary constant, is true, that is what we are talking about. So, if you were to assume some arbitrary constant and you are able to prove a predicate with respect to C, then it is true for all existing elements in the domain. Right? So what do we see the relationship between these two? This SC that we see over here has to happen inside the subproof where C has been introduced as an arbitrary constant. Right? So this rule is only going to work in the subproof given a constant to work with. This comes from the fact that we say that predicates do not have a truth value on their own. Predicates do not have a truth value on their own. Right, existential. So existential quantifier says if the moment that you have got anything with respect to an arbitrary constant or to some constant, then it means it proves the existence. It proves the existence. Right. So we see that this is happening if we are looking at SC. SC needs for you to have introduced C to begin with. So how do we do that? We've got C, SC like that. Then we introduce C with respect to SC. So this is, say we're given this guy. We introduce C and we substitute the variable C for the constant C. And then we apply all the natural deduction rules. Right? If we are able to prove anything Q, because we know that they exist, something based on an arbitrary constant, it means that it is true that if we're able to prove something, it should be true because of the existence of an element that will make Q true. Therefore, Q has to be true. So again, this SC is going to be found in this subproof and it leads to some X SX. Right. So those are the 4 natural deduction rules. Let's look at some questions. Right, so we have got some hungry and we want to prove some hungry and some student is hungry, and we want to say some are students and some are hungry. Right. So what do we do? The first we start with the premise. And hungry X. Right. So this is a premise. Next, we have to go and say, all right, so we've got an existential quantifier. Let's open a subproof. Say with respect to C, then we're going to have student C, and hungry C. Right. The number 3, we're going to have student C and hungry C. Conjunction elimination, we have student C. Number 4 also have hungry C. So conjunction elimination on number 2, conjunction elimination on number 2. Then number 5, I'm going to have some hungry students because I've got some student, I've got student C. So I'm going to have some hungry X. So I'm going to have existential intro on number 3. Number 6, I also have hungry X. There'll be existential intro on number 4. Then number 7, I'm just going to have the conjunction of these two. And hungry. So from this assumption of C as an arbitrary constant, I've managed to prove some students, some are students and some are hungry. So then I come to number 8 and I'll say X, student X and hungry X. So this is going to be existential elimination from number 2. Number 1 was the existential statement, then number 2 to number 7. All right. So this will be the solution for that using those two rules. So we've used existential elimination so far. Then we'll see if we move over to say this prove they're contradictory. They're saying prove that they lead to a contradiction. This is a premise, this is a premise. Number 3, I will have, so likely I'm going to start with having that C is subproof C, then I have clever C. Then number 4, I will have, if I have clever C, I can have not clever C. So now I'm using this elimination. This is an assumption. Then number 5, I'll have not clever and clever will lead to a contradiction. So this will be contradiction intro on number 3 and number 4. Then number 6 is going to be a contradiction, and this will be existential elimination on number 2, number 3 to 5. Like that. Right. Right, we want to prove this as well. So we are seeing a pattern. Every time we have to prove something with an existential quantifier, we have an existential quantifier at the beginning. So we are starting to see a pattern image. So let's see number 4. So these ones are premise, premise, premise. So we're going to have C with respect to T, TC. Then number 5, I'll then say I'll remove this and that. So I'm going to have PC O Q C implies RC and SC. Then number 6 I'll have, so this is elimination of the universal quantifier. So that will be this will be on number 1. Number 6 will be also, we have TY or R, sorry, not TY. We are under the domain of C, so we're going to have TC or RC implies QC. Elimination on number 2. So we now have everything in terms of C. Number 7, we have TC. We can have TC or RC. So this will be O introduction or number 4. Once we have that number 8, it means we can have QC. So implication elimination on number 6 to 4. Then number 9, once I've got QC, I can have QC or PC. That's another O intro on number 8. And then once I have that, I'm going to have PC and RC. So we're going to have RC and SC, that's implication elimination. Number 5 and number 9. Then from there, number 11, we've got RC conjunction elimination on number 10. Number 12, we have RC, so number 12 gives us, we have RC and TC, so we're going to have TC and RC. Right, so this will be implication elimination or conjunction introduction. Number 4 and number 11. Right, and then we have TX and RX. Now that's existential introduction on number 12. Then from there, number 14, we can now conclude TX and RX. And this is existential elimination on number 3, number 4 to number 13. Like that. Right, next question. Right, all students or all are hungry implies that all students, all are students or all are hungry, like that. So we want to prove this. So what we do, we have got number 1, or hungry X, right? So from here we can go and say so this is a premise. Number 2, we can go and say, okay, this is what we have. We've got an OR statement, so we can have OX student X. This is an assumption. Then number 3, we're going to have, in terms of C, we make an assumption in terms of C. Then number 4, we have student C. That's all elimination on. Number 2, then number 5 is going to be student C or hungry C. So that's all introduction on number 4. And then number 6 is going to be, out of this, we have that, so we say OX student X or hungry X. Like that. So this is the first side of the disjunction. Now let's go to the second side of the disjunction, where we see we're going to repeat more or less the same thing. Number 7, we're going to say OX hungry X. And then number 8, we say is based to C in assumption. This is also an assumption. Number 9, we have hungry C. And then after that, number 10, you're going to have O going to have student C and hungry C. O, sorry, it's an O, hungry C. Right, and this is all introduction on number 9. Then number 11, we can then exit this. We have right, number 11, we're going to have outside of the subproof OX student X or hungry X. That's all intro on number 11. So from the first one, we've managed to prove the exact same thing, same as the second one. We can then come and say student X or X student X or hungry X. Right. And this is as a result of O elimination. The first statement within O is number 1. The first subproof is number 2 to 6. Then number 7 to 11. Right. So that is that. That is that. Let's look at something like this, proof from no premise. So proving from no premise is only going to happen when it is an implication. So you just start by a subproof, right? So in this subproof, you assume this to prove that. So you assume right? And then we need to prove that. So given this assumption, we can see that if we want to prove OX PX implies QX, so it means we need to assume and prove OX QX. So once we have this number 3, we can then say, okay, cool, let's do everything with regards to C assumption. Then number 4, we're going to have PC. Number 5, we strip this, so this is all elimination on. But 2, so we say we remove from number 1, we're going to have PC implies QC. Right. Then we have, so this is going to be or elimination, inverse elimination on number 1. Then from 6, we can have QX implication elimination on number 5 and 4. Right, and then we have QC. Our goal is to prove that, so we can say if we've proved PC, then we can say number 7 OX or XQX, and this is C to QC. C to QC. That's that. So this is all intro. Universal introduction. And then from there to there we have AX, PX. Implies QX. So this is right. So that becomes of that. And then number 8, we simply have OX, PX. Right. So let's write this neater. OX, PX implies QX is a whole implies OX, PX. So this is what you're going to have. Right. So let's stop here. And it's enough practice for you. You can try as many as you can and then send them to me. Thank you very much for attending. Goodbye.